Hello everyone, welcome to this video in which we will talk about discrete probability laws. By the way, there will be 3 different videos on discrete probability distributions, so you can say laws or distributions, talking about hypergeometric distribution, binomial distribution, and Poisson distribution. So first of all, let's remind what a probability distribution is. So, what is the context of this term? The context leads in a random experiment into which we have to try at random several times the same experiment, or the same or quite the same. So let's examine one example. Let's take 2 dice and let's roll them and note the total result. Okay, so we have to add the results. So if we roll 2 dice, 2 6-sided dice, of course, the result can be this sample space, 2, 3, 4, 5, and so on. Okay, the double one gives you a total of 2, the double 6 a total of 12, and between these 2 extreme results, you can obtain every single integer. Okay, 3, 4, 5. You can obtain an 8 by a double 4, or by a 3 and 5, and so on. So let's now create a partition of the sample space, which is not obligation, but that we will create here in this example. This partition is designed by 3 events that will be less than 7. Okay, your total is less than 7. Second possible event from 7 to 10 as a total, and the third and last event 11 or 12. So you are rolling your 2 dice, note the result, so the total, and you're asking whether you are in E1 or E2 or E3. So it's a random game, okay? And we have to put something else, something additional, that is a gain. A gain is designed here by the letter X. That is a random variable. So let's decide some gains chosen as we want, as we wish, concerning every of the 3 different events that are a partition of omega. For the event E1, let's say that you will lose 3 euros. If you fall in event E2, you will win 1 euro, and if you fall in event E3, you will win 5 euros. So the question is, do you have an interest to play this game, and to play this game a lot, okay? Or do the organizer have an interest to put this game online and to have a large number of players? Will the organizer attend or expect to win money thanks to these gains and losses for the players? So we have to make every single value of x, every gain or loss, in front of or corresponding with the probability it would occur. So let's put again the values of x and calculate the probabilities of each one of these values. If you know what happens when you roll 2 dice, you can conclude that there will be 36 possible pairs. 1, 1, 1, 2, 2, 1, 1, 3, 3, 1, 2, 2, and so on until 6, 6. There are 36 possibilities. Some of them lead to the event E1, some of them lead to E2, and some of them lead to E3. So the question is, how many of them? Okay, according that, it's a fact that every one of the 36 pair is equally likely compared to the others. So everyone has a 1/36 chance to occur. This way, you can say that you've got 15 chance over 36 to lose 3 euros because there are 15 pairs that lead to the event E1, less than 7. There is the 1-1, the 1-2, the 2-1, the 1-3, the 3-1, the 2-2, and so on until 6-15. The number of possibilities to win 1 euro is 18 over 36, of course, and to win 5 euros, only 3. You have to make a total of 11 or 12. That is reachable thanks to a 5-6, a 6-5, or a double 6. Only 3 possibilities over 36. The fact to put every value of a random variable and corresponding with every probability of each value is to establish the probability distribution of X, which is the title of our chapter. So this is in front of your eyes in this table, the probability distribution of X. This example is a genuine example that is not seen in other games. Okay, it's a special game with special rows. So this probability distribution doesn't have a name, for example. It's not binomial, or it's not hypergeometric, and so on. So it doesn't have a name, and you have to put by yourself every values that are interesting here. So now, what can we get from this table as results to help us to make predictions on your interest to play the game? The first thing we have to know is the law of large numbers. The more you play, the closer the frequencies of events are to the theoretical probabilities. These probabilities doesn't tell you that you will effectively lose 3 euros 15 times every 36 games. But it's an average that you will obtain if you play this game a lot. So the more you play, the closer the reality of events are to the theoretical probabilities. So you can expect on average to lose 3 euros 15 times every 36 games, to win 1 euro 18 times, and to win 5 euros 3 times. So you can make a calculation of your average expectation in terms of losses and wins every 36 games. So the result is to lose 12 euros, okay? 3 times 15, that is 45, 18 times 1 euro, and 3 times 5 euros. So 18 plus 15 will lead to a win of 33 euros, but you've got here a loss of 45 euros. So as a total, you will lose 12 euros every 36 games on average. These considerations lead to a value that is reported to one game. 12 euros every 36 games means 12 divided by 36, 33 cents approximately per game of loss. Of course, it's a negative number. So you can expect to lose on average, of course, 33 cents per game if you play a lot this game. So as a player, you will be a loser in long-term play. And as an organizer, you will be a winner. This first parameter of negative 0.33 is called the expectation, or the expected value of the gain, so of your random variable. A second parameter, which is very important for us, is the standard deviation. That is, so the mean fluctuation or the average variation of your gain from one game to the following. And you can enter this table in your calculator to obtain the standard deviation, sigma, which will value approximately 2.5 euros, okay, 2.494. So it means that on average, the variation of your gain from one game to the other, okay, by going into this table several times according to the probabilities, will tell you that the variation of the gain -3 to 5, 5 to 1, 1 to 1, 1 to 5, 5 to -3, and so on, will be approximately 2.5 euros. So it will be important for us, and we will see in spatial probability distributions how to use it. So now, let's go to what is called the hypergeometric law. This first example was a general example. Now let's create some special games rules that tell us that we are playing several times a game into which only two outcomes are possible. In the previous example, let's go back to the example, there were 3 possible outcomes to the game. And this kind of situation is not associated with a certain name, okay? But if you create a game into which you've got only 2 possibilities each time, and if you play this game several times, okay, n times, you will be able to create a probability distribution that has already been created. This time it will be called hypergeometric distribution, and we will see why. What are the characteristics of this distribution? So let's take the first exercise of our document that tells us about taking letters in the alphabet. Our object, our initial set into which we have to draw letters, is our alphabet that is composed with 20 consonants and 6 vowels. So there is a partition inside our initial set. Now let's take some letters. The experiment is to choose at random 8 different letters. So you just put your hand into the bag and take or draw 8 different letters. The fact to draw 8 different letters at the same time, a simultaneous draw, leads to combinations if we're talking about counts, okay, about combinatorics. So we are in a very special case, and we have to create a random variable in order to be able to talk about the probability distributions, as we've seen earlier in the example. So here, our random variable will be the number of vowels among the 8 drawn letters. So this time it's not a gain in euros. We're not playing a money game, okay, but only the number of some category inside the initial set. So our interest is to count the vowels. Okay, so let's say now what could lead to what we call the hypergeometric distribution. The first point, which is a moot point, is that the object's initial set is partitioned into one subset and its complement, only 2 complement subsets. Successes and failures, here, vowels and consonants. Now, the second point that is very important for us is that the experiment consists of 8 draws. That is a number that we will name n. And this draw is made without repetition. We have to choose 8 different letters from the alphabet. So repetition is forbidden, which is a very important point for us. The third point that has been given in the statement here is that the random variable will count the number of vowels that will be the number of successes from our initial set. So your random variable is not here to count something else, some gain in euros or something else, okay? But only the number of interesting objects that you can get in your draw. This way, if the 3 points are met, you can talk about hypergeometric distribution. That is a set of formulas that give you, for example, the possibility to calculate the probability of having 3 vowels inside your 8 letters, or 2 vowels, or no vowel, and so on. So the notation is this one: a distribution of x, number of vowels among the 8 letters, is then h hypergeometric 8, 6, 26. Okay, so I hope that you will have a better understanding on that at the time in the next video where we will compare this distribution to the binomial distribution. There are 2 cousin distributions, in fact, and then by the comparison of both, you will be able to show or to find out the differences between both and to understand and have a better understanding of 2 laws. So let's just use the formulas that are given for hypergeometric distributions. So we've got here a distribution that shows 3 parameters. It can be 2, okay? It's 3 parameters for this distribution, 3 necessary numbers that have to be mentioned in order to be to calculate, everything you want, every probability, the expected value, the standard deviation, and so on. The first parameter is the number of elements that have to be drawn. The second one is the number of success elements in the initial population. And the third parameter is the total number of elements in the initial population. This way, in this law, the probability to get a certain number k of successes after n draws is given by this formula, which is not obvious. But if you have a closer look to this formula, you can see that you already encountered this kind of calculations before, okay, in a previous video where I talked about combinatorics, and especially in the part combinations and partition. Okay, so you can go back to the video combinatorics and to the end of this video talking about combinations and partitions. In fact, you've got 3 different combinations to calculate here. The first one refers to the successes. And I put the values corresponding to our exercise to be more clear. C sec k means that you want to calculate the number of ways to choose k vowels among the 6 that exist in the alphabet. The second combination number refers to consonants. You want to be able to calculate the number of ways to choose 8 minus k consonants between or among 20 consonants in our alphabet. This multiplication leads to the total number of ways to choose k consonants and 8 minus k k vowels, and 8 minus k consonants in the alphabet. So that corresponds to our event x equals k, that probability we want. Okay, below that, you've got a general combination number that is the total number of ways to choose 8 letters among 26. That's all. 8 different letters, of course. So now we can calculate the probability, for example, and I put back here the way to obtain a combination number in your calculator. Occasion on the left, Texas on the right. The fact to calculate P of x equals 0. F x is 0. So what is the probability that among your 8 letters, you've got only 8 consonants and no vowel? X equals no. So you will have to put 0 on the combination number of vowels and 8 on the combination number of consonants. But the only numbers of parameters that change if you change this value for your given probability in the formula. The result will be approximately 8%. Okay, your probability to get no vowel is 8% approximately. The probability to get 3 vowels is bigger. Okay, it's almost 20%. And of course, you just have to put a 3 for the combination of vowels and a 5 for the combination of consonants in your formula. So you can obtain like that a series of results as probabilities, and why not for every single value of success that you want. A third question existed in this exercise that asked us about the probability of x equals 8. And of course, x equals 8 would consist in placing an 8 here in a combination number that is impossible. The number on top of a combination, it must be less than or equal to the number of the bottom. So at maximum, it will be a 6 here. And of course, if you take 8 letters in the alphabet, 8 different letters, you can't obtain more than 6 vowels because there exist only 6 vowels in the alphabet. So the event x equals 8 is impossible. In a hypergeometric distribution, regarding that, we are processing to draw without repetition. The number of possibilities as a number of success are limited to the total number of success elements that exist in the initial population, of course. So now let's establish a list of results, but before I forgot, let's calculate the expectation. So the expected value of such a law is given by a very simple formula, n times a divided by n in capital, so 8 times 6 divided by 26, the result being 1.8 approximately. So if you were in a nameless discrete probability distribution, you wouldn't have access to such a simple formula. You would be obliged to fill the whole table of values of x and probabilities below them, okay? And then calculate the sum of probabilities times values, sum of pi xi, and so on. And you would obtain E of x. And that is something that we could do here in a hypergeometric distribution. But in this special case, this formula gives us quicker result, okay? So now let's analyze and comment this result. The expectation of x. X is a number of vowels, so E of x is a number of vowels as well, 1.8. So it's the average number of vowels that you can expect if you play this game a large number of times. So if you choose 8 letters at random from the alphabet And if each time you note the number of vowels you got, if you play this game a large number of times, you've got a long list of number of vowels that have been obtained, and the average number of vowels will be close to 1.846. This is the expectation actually in the reality if you play an infinite number of games. But the more you play, the more the reality will be close to this number. Okay, second way to comment this value, getting 2 successes after 8 attempts is the most likely to occur. So clearly, the most likely, if you take 8 letters in the alphabet, is to get 2 vowels. Okay, getting 3 vowels will be a little bit less likely. Getting one vowel will be a little bit less likely, and so on. The more you go far from this number, the lower will be the probability to obtain the desired number of vowels here. So, why 2 vowels? Because 1.846 is close to 2. Okay, and if you try your draw only once, you can get only an integer as a number of vowels, of course. So you have to choose the closest integer to the expected value. And this time you can say that this will be your likeliest event. So now let's have a possibility that is more interesting to proceed to a forecast of what could occur if you take 8 letters from the alphabet, thanks to the standard deviation. So there exists a formula in the hypergeometric distribution to get the standard deviation without the knowledge of the whole set of probabilities. This formula is not very simple, but this is an advantage because you already know all of the 3 parameters that you need. They are here, 8, 6, 26. So you just have to place them at the right location in the formula, like this, and you will be able to calculate the result as a standard deviation. So it's approximately 1, okay, 1 vowel. What is the meaning of the standard deviation? So once again, this is the average variation of number of vowels that you can obtain from one try to the following, one trial. So if on average you can expect to get approximately 2 vowels, you can also expect that 3 vowels or 1 vowel, so a 2 plus 1 or 2 minus 1, will be likely evens too, okay? Because being inside the interval and close to the average value, and not so close, but at a maximum distance of 1 standard deviation of the average value, leads to likely events, and much more likely than events that are not inside this interval. So 2 vowels is the most likely or the likeliest event, but 1 vowel and 3 vowels are likely too. And of course, this means that no vowel or 4 vowels or 5 and so on are very unlikely events, or much more unlikely than the 3 events that are at the center of the possibilities here, 1, 2, or 3 vowels. So why is it so dissymmetrical? You're choosing 8 letters. You could expect that your average as an expectation would be 4. Why not 4 since you've got 8 letters? Because in the alphabet, you don't have the same number of vowels and of consonants. There are only 6 vowels and there are 20 consonants. So it's some kind of logic that you can't expect to reach the same number of vowels and the same number of consonants in your sample. In fact, you can expect on average that in your sample there will exist the same proportion as in the alphabet. So 6 on 26 is the proportion of vowels in your alphabet. So it's like, and this calculation leads to the result, 1.8 vowels out of 8 letters, okay? And in fact, this calculation is a proportional calculation or a cross product, if you want to tell it this way. 8 times 6 divided by 26 is the result of the fourth value that misses inside a 4 cells proportion table. That's all. So your expectation is, let's say it again, is that the number of successes you get in your sample corresponds to the right proportion compared to what does exist in the population. So to change the example, if in a population of people, 30% have a driver's license, for instance, and if you interview at random 100 people, your expectation is to have 30 success, okay? Because in the population, the proportion is 30%. So to have 30 people that have a driver's license among the 100 people you interviewed. Now let's create lists inside our calculator to get the whole list of probabilities and to have a look on the total probability distribution in a hypergeometric law. So you can use your calculator in list mode. You could use it in a function mode with x and y, of course, but let's take a statistics mode, for example, here, that will help us afterwards to calculate the expectation as a mean and the standard deviation, okay, by using the statistics mode. So you have to put this way a list formula, and this list formula, in order to obtain the probabilities here of each kind of event, will correspond obviously to the formula of the probabilities. So in black here, and especially for the Texas calculators, we'll follow the formula with the three combinations of the calculation of a probability. The ones among you that owns a Casio are lucky because your Casio knows about the hypergeometric distribution. Hypergeom PD, punctual distribution, is the tool to be used here, and you have to give your calculator the right parameters. The number of success will be found in list 1 and is a variable, but the parameters of the law are 8, 6, and 26. So how do you find on the Casio the tool hypergeometric? So if you go at this place, okay, to create a formula, you can activate the key option, okay, on the top left of your calculator. And in the screen, you can choose the item stat and then the sub-item dist, like distributions. So option stat dist, and then you can reach some different discrete probability or continuous probability distributions. Among them, you can read HGEO, okay, for the hypergeometric distribution. So you have to choose HGO and then to choose HPD, okay, in order to calculate the probabilities of some given number of successes. So I will have an occasion to tell you about HCD or BCD for the binomial distribution later, okay, when both calculators will be able to talk about the same probability distribution. The hypergeometric distribution is, if I remember well, the only one that is not in a Texas, but that is in Acacia. So after having entered this formula, you will get these results. Of course, no result for 7 or 8 successes because it's impossible. At maximum, you can get 6 vowels. And these are these probabilities. You can recognize the value 8% approximately for no success and approximately 20% for 3 successes. So you've got here the other values of the probabilities. And you can recognize as well that the probability that is the biggest is the one that corresponds to 2 successes. Okay, that was the number of successes the closest to the expectation. So it's a fact that it's a big probability for this number of success. And it's a fact as well that the probabilities of 1, 2, or 3 vowels are very big compared to the other possible events. Okay, at maximum it's 8% for 0 vowel, 4% for 4 vowels, and 5 and 6 vowels have a very, very low probability. Let's graph them in order to see them well. So no success, 8%, 1 success, 2 successes, 3 successes, and so on. So the calculations of the expectation earlier, of course, and of the standard deviations, let us to think about the situation without graphing it. So now we've got the graph in front of our eyes. We can confirm that, yes, it's fact, indeed, the 3 probabilities here of 1, 2, and 3 successes are very big compared to the others. And if we group them, we can see that we've got 30%, 37, so 67 in total, and 20, 87% of probability to be here, compared to only 13% for the 4 possible other events. So that is what we can do on a hypergeometric distribution, but the most difficult, in my mind, is to recognize a hypergeometric distribution. So to begin an exercise by being sure of the law to use. Okay, it depends on a good reading of the statement of the exercise, and it will be very important. We will have some exercises in a tutorial video for that. So thank you for having followed this video, and I can tell you, have a good day.